welcome back to Question Field, the place where you ask the questions and we field them. I am Brian.
And I'm Campbell.
And Campbell, I was thinking about it, Campbell. The place where you are in the world right now, right? If there were two land masses and you were to build some infrastructure between them, and I were to go visit that, right? I could say I came to Cam's Bridge in Cambridge. I could say that. I probably wouldn't.
Really could. It's even better actually because the river in Cambridge is called the River Cam, hence the name.
Really?
So you would be visiting a bridge over Cam with Cam in Cambridge.
There we go. Ladies and gentlemen, this is
what an intro.
What an intro. This is part 2 of our discussion on quantum computers because we literally could not get enough. So we are back to try and make some more sense of this. And so I highly recommended that you go back and listen to episode 1. But quantum computers is also one of those things where, if you jump in just right here, you'll probably catch on pretty quickly. And it's very difficult to understand anyway. So do what you want. We're not your parents. Do whatever you want. There are no rules. All right. So Campbell, we were talking about topological superconducting quantum computers.
I did mention that at one point. Yes. In the last episode. And
so, as if quantum computers weren't enough, we added topological superconducting. So
there are a few words that we should break down in that phrase.
Yes. So the question for Question Field this week is, what?
What?
That's
a good question. It's one of my favorites, I think. So the answer to the question what is very involved. There is also the question why, and
as well as where and how. And
that's true. Yeah. So maybe it could be good to start with the why, and then that maybe gives a bit of motivation for the what.
Sure.
So before last episode, we were talking about qubits, thinking about qubits as these arrows pointing around in space at this, at some point on a globe. And we were also talking about computations that you can do with qubits. And so the way that you do those computations is that you start with some initial state. Maybe all of your qubits are pointing in the up arrow state, they're pointing upwards. And then you do some gates on that state. So those gates can involve rotating the qubit arrows. Maybe they involve making some entanglement between the qubits, some other mysterious things. Mm-hmm. And then you do some measurements and you get an outcome. And so that's a quantum computation. That's all that it involves. And
easy.
We very glibly said, that's it. That's all that you need to do. Obviously, that's incredibly difficult. And one of the reasons it's incredibly difficult to do this stuff is that when you have some physical manifestation of a qubit, you maybe have an ion or you have a photon, that is an incredibly fragile system. You can have a little bit of what's called noise, environmental noise, come along and give it a bit of a jostle, and all of a sudden your qubit can be in a new state, or it can be in some random state that you don't really know. Or maybe you just don't have very good control over your qubit. Maybe you want to do a rotation by 45 degrees, and instead you do one by 49 degrees or something like that. Mm. And over time, maybe those errors add up and just destroy the information and make your quantum computer useless.
So it's kind of like the equivalent of having a Walkman in the 90s, and it's just like, any bump and your CD would skip, and it's kind of
yeah, the Discman, right? The thing that you would try so hard not to rock, and then if you're in a car or something, you're screwed.
So same thing. Okay,
it's exactly the same. Yeah. But I mean, there is an analogy with CDs that we could make. For example, we were actually talking about CDs, a couple of episodes ago. And one thing that you could do to protect your information from, for example, scratches, right? I mean, you can scratch up your CD and it can still be readable. Maybe this is showing our age. Maybe this is not going to be accessible whatsoever to the
so
to
kids,
the younger
back
generation.
In the day when Grandpa Brian and Grandpa Campbell were growing up, we had these shiny things.
That's it. So anyway, you can scratch them and they'll still be readable. So scratching a CD is kind of like introducing some noise into your system. The way that you make your CD readable when you scratch it is to repeat your bits over and over again a bunch of times. If you want to have a 0 on your CD, so in one of your bits you want that to be a 0, well, instead of just doing 1 0, you have 5 zeros or something. And if one of your zeros gets flipped to a 1 or just gets corrupted in some other way, you can't read it, well, no worries, you've still got 4 other zeros there. Maybe if you read 1 0 0 0 0, then you'll be like, well, in all likelihood, there's been something that has occurred here on the first bit that's flipped it from 0 to a 1, and I'll just flip it back to a 0, and then I'll be fine. Hunky-dory.
Right.
So that's something like that is what we would like to do with a quantum computer. One thing that you can do is to use what's called a quantum code, which is quite a... It feels like a very
the newest novel from Tom Clancy.
That's true, yeah, quantum code. So a quantum code is the analog of that repetition that we did with our bits. So if I take one bit, a 0, and I repeat it 5 times, that's like a code. I encode the information of a single bit into the state of 5 bits by just repeating it. It's a repetition code. It's the same thing as if I really want to get my point across, I say the same point over and over again.
And if you want to really get your point across, you say the same thing over and over again.
If I really want to get my point across, I say the same thing over. Okay. Oh yeah, this is a terrible joke. But yeah, that's right. So okay, so that's one route to dealing with this problem of fragile quantum states. Use a quantum code. That's a perfectly good option.
I'm about to hear a big however, though. That's
however, you can do something else, and you can find physical systems that can encode your qubits that are impervious to noise by their very nature. So this is this very exciting thing about topological superconducting. Quantum computing is that the superconductor that you use to store your qubits, is really impervious to noise. It's like incredibly resilient. So that's the sort of why. That's the pitch for topological superconducting quantum computing.
Right. Yeah. Right. Because it ultimately comes down to we want our results to be as close to right as possible.
That's right. Yeah. So if you have some noise in your system, and this noise can be, maybe the environment that the qubit sits in comes along and somehow makes a measurement of the qubit before we want it to. So then, or if you remember from last time, a measurement changes the state of the qubit. Maybe the qubit is initially pointing to the right, and then after the measurement, it points up or down.
Right.
And then you can imagine that if maybe if we're doing some complicated set of gates on our qubits, then if I measure one of them, that's going to change the output probabilities that I have of my answer. So, for example, if the environment measures the first qubit and it gets the output 0, this is a very hand-wavy way of thinking about this, but loosely speaking, then it's much more likely that the output of the computation is going to have 0 in the first measurement slot. I measure the first qubit to be in the 0 state.
Right.
Or maybe it flips the qubit from being pointed up to pointed down, or from pointed right to pointed left, or that's all possibilities that the noise can do. Yeah. And so the reason that we care about it is that we want to actually do these computations and get the right answer, is exactly what you said.
Yeah.
And so do the words topological and superconductor mean anything to you?
Let's start with superconductor. It has to do with taking some element, and I believe they need to be chilled to near absolute 0, perhaps?
That's right. Yeah.
And
for most of them.
What is the element of choice here? What is if you could choose which element you would use for your to chill? What's at the top of the menu?
Well, that's a very good question and a very difficult one. For example, most metals, when you cool them down to cold enough temperatures, will superconduct. for example, aluminium superconducts.
That's aluminum
And-
for us here in the States.
Oh, yes, sorry, I forgot that there's also people that pronounce it incorrectly. And, okay, so most metals superconduct. There are also sort of compounds and complicated ceramics that when you cool them down will superconduct. But what does it actually mean to superconduct?
Well, I guess to superconduct would be to conduct, but much better. Would be my...
Yeah, that's right, yeah.
There we go.
So usually we think of current flowing, and when current is flowing through a circuit, there are a few things that we usually have. We usually have voltage, right? And then there's current, and then there's resistance, right? And if you have all those things, usually you have Ohm's law, which maybe you know about.
Oh, love Ohm's law, yes.
Yeah, V equals IR. So anyway, these things are related to each other. In a superconductor, your resistance is 0, which is quite weird. And it's very weird, in fact. You can set a current in motion, and it will continue to flow forever. So there's no voltage drop that's happening.
Right.
But it's keeping on flowing. So okay.
That sounds like one of those things where mathematicians hate superconductors for what they do to Ohm's law.
Yeah, that's right. But no, anyway. But yeah, that's the idea. And it's usually in physics, we say something is 0, and what we actually mean is it's very close to 0. Or we say something is, I don't know, 1 or equal to pi kilograms, and we mean, well, plus or minus 0.001 kilograms or something like that. Right. But really, in superconductors, it is as close to 0 as we can confidently say. You know, it is basically 0. You can set this thing going and come back in 10 years, and the current is still going to be flowing. So it's pretty exciting, pretty weird. And what's going on here is superconductors are fundamentally quantum mechanical objects. The reason that they allow for current to flow indefinitely is a quantum reason. And so we don't really have the time to go into the depths of what superconductors are and how they work. And part of the reason is that we don't necessarily have a great understanding of how superconductors work in all situations. But basically, this is this is the feature that presents itself most strikingly. The fact that you have current flowing indefinitely. Okay, so that's superconductors. We also have the word topological in that phrase from earlier. So what does that mean to you?
All right, so I mean, I feel like topology, when I've come across it ever, it has to do with how many holes does a straw have, that kind of...
Yeah, those sorts of questions, exactly. Like donuts and coffee mugs and stuff. To just explain for the uninitiated what I was saying before.
I'm the uninitiated.
So if you have a donut and maybe it's made out of Play-Doh or putty, I can stretch and mold and squish this putty into the shape of a coffee mug without tearing the putty at all. And the reason that I can do that is because they both have one hole or handle. So the coffee mug has a handle, but that is effectively the same thing as the hole in the center of the donut.
Right.
And so, yeah, that's this topological feature of...
so it's essentially
surface.
saying that there's like two classes of features that an object can have, and like there's this more... The more fundamental one is the fact that you need to, like, in this example, you need to have a hole. You need to have that hole somewhere. And then on top of that class is the second class, which is do whatever you want, and it can look like whatever, as long as you still have your one hole and that doesn't go away.
Yeah, that's a great way of thinking about it. So to rephrase what you're saying, you have geometric features of an object, like a shape, a donut one, right? And these geometric features are not stable to sort of deformations that you can make of your shape, right? If I sort of put a little dent in my donut, then all of a sudden the curvature around that region of the dent is changed, and maybe the surface area of the donut is changed, and so on and so forth.
Sure.
But then on top of that, you have topological features, and those features, such as the number of holes that you have in your shape, those do not change when you make small deformations. So what's going on here is that you have a number which characterizes your shape, right? It's, for example, the number of holes that the shape has. And that number doesn't change when you squish or stretch the shape, when you make small deformations of that shape.
Okay.
And this same property is found in physical systems as well. So I can find numbers that describe the state of my system. These are called topological invariants, very analogous to the number of holes in a 3D shape, like a donut. These numbers, these topological invariants that characterize the state of my system, also don't change when I make small deformations to that system.
Right.
So in the physical case, the deformation is going to be something like changing some parameters slightly or applying some fields or something like that. If we go to the case of superconductors, of topological superconductors, there is a number which characterizes the state of my system, and that number cannot change when I only make small deformations, small sort of manipulations of my system. It's sort of stable. It's this like really stable property of my system. And this is going to be the crucial fact that is going to mean that our system is really resilient to noise, and is very, very useful for quantum computation.
Well, I guess so I'm assuming that there are these quantum computers that do not utilize the potential benefits of the topological superconducting, what those quantum computers are doing. So, and our aim is to reduce noise. So if I was a little more on board with how having the no resistance, like I understand that. I don't understand, but my intuition is helping me kind of see where that could be useful in helping reduce noise. So what is the topology? Where is that connection?
So I think this is probably most easy to answer by talking specifics as opposed to broad, broad hand wavy stuff. So the specifics are kind of funky. So what we're dealing with here is not three-dimensional chunks of superconductor. What we're dealing with here is either two-dimensional wafers, like very, very, very thin sheets, or one-dimensional strands or nanowires of superconductor. So very, very narrow wires, something like that.
Right.
And the sorts of phases that we're interested in only appear in these two-dimensional or one-dimensional systems. Okay, so that's the first thing. But we're sort of building up to the main result here.
Yeah.
So maybe the easiest thing to talk about is what I'm maybe more familiar with, which is the one-dimensional case. And so this is actually existing in labs today. So this is quite exciting. But there are labs in the world today with these tiny little nanowires, which are nanometer thicknesses and like tiny. And these nanowires superconduct so they can have charges flowing within them with no resistance. And like I said before, what it means to have this superconductor in a topological state is that there's a number that characterizes this system which doesn't change when you sort of perturb that system, right? It's this topological invariant. Okay, so now I've sort of built up to be able to describe exactly what this number is telling us physically about the system. So this number can take two values. It's either 0 or 1. In our superconductor, there are energy levels that our electron can sit at. And this number, this topological invariant, is describing the number of these energy levels that are exactly at 0 energy.
Okay.
So if this number is 1, I can put 1 electron into my system without adding any energy to that system. And if that number is 0, I can't do that. So it's describing the number of these states that an electron can sit in that are at 0 energy. But that's just the sort of first pass at understanding this topological state in a nanowire. The reason that there is this 0 energy state for an electron is because there's something funky going on at the ends of the nanowire. So the strange thing that's going on at the ends of the wire is that there are what are called quasi-particles that sit at each end of that wire when you're in the topological state. So have you come across this word quasi-particle before?
So, I mean, particles could be their own episode, all on their own.
Absolutely.
I guess in the quantum sense, particles are represented in these, or they are like an artifact of fields that permeate, and again, like the thing that I've picked up over the years is that particles could be thought of as like excitations in these fields. And so when you talk about a quasi-particle, are we talking about like somewhat of a perturbation in these fields, but not really, or is it like
it's like
a potential?
It's like the field itself is somehow a collective phenomenon of a more fundamental system. So in the superconductor, you've got all these electrons moving about, and you've got some metal ions maybe that are also sitting there in a lattice, and you've got this sea of electrons that are moving in between the ions. And something about the collective motion of these electrons can produce little things that are, little, I don't know, eddies, or you can think about maybe vortices, or, swirling currents or something like that, which we can think of as themselves particles. And it is quite confusing to think about. So I think maybe this, again, deserves its own episode, as you say. But yeah, for example, sound, right? Sound can move through a medium like a crystal or a block of brick, or I don't know, something, by propagating waves, right? Maybe if all of the atoms are in a lattice, then as a sound wave comes along and hits the boundary of this lattice, it sends the first row of atoms in a little bit, which then bumps the next row, and then you get this propagating wave passing through the material. So you can sort of think of these waves as being particles in and of themselves, in the same way that photons, which are waves in the electromagnetic field, are particles.
Okay.
So these waves are called phonons because there's presumably some Greek connection there. I don't know. Something to do with sound as opposed to light. Maybe thinking of the phonon case, there are sort of two different descriptions that you could have of that system. You could think of it as either a lattice, which is vibrating in some way, or you can think of it as just a box with a bunch of phonons in it.
Okay.
And the phonons are waves that are bouncing off the sides of the box or something like that.
Right. Okay.
That's the sort of idea. But the take home is that there is something strange again happening at the ends of these nanowires, these superconducting nanowires, and we can think of that strange thing as being the presence of a certain type of particle, certain type of quasi-particle, which again is just some collective phenomenon, collective motion of the electrons and that kind of thing. Okay, so at this stage, I'm going to introduce an analogy which is pretty odd, but I think it's going to maybe help to understand things. So one of these particles, which is called, by the way, a Majorana fermion, or just a Majorana, that's like spelled Majarona. So it's named after an Italian physicist who came up with this idea for a particle. And okay, so we can have these Majoranas, which are sitting at the ends of the nanowire. And the way to think about these Majoranas is that it's like each of them is like half of a house. It's like a house which is split in two, split down the middle. Which means that if I have two of these houses, or two of these half houses, I can kind of bring them together and form a whole house, right?
Okay.
So if I have two Majoranas, I have a whole house, and there's something that can live in that house, and that is an electron. Okay. So it's a very weird system, but okay. So we've got these Majoranas. They're sitting at opposite ends of a nanowire, and if there are two of them, then I have a house that an electron can either inhabit or not inhabit.
Okay.
With me so far?
Yes.
Okay. And the reason that this is exceptionally weird is that these Majoranas can be very, very far apart. This nanowire can be really long.
Yeah, so if you have the two of them, the electron would have to be... Where would it be? it would have
Yeah,
to...
where is it, right?
Yeah.
So it's, yeah, you can think of it in different ways. Maybe you want to think of it as sort of splitting in half, and these two electron halves are each sitting in their own half house. Or you can think of it as being 50% likely, or there being a 50% probability that it's sitting in this house,
Or the other one.
sitting in this
Half house.
position here at the end, half house, exactly, or in this half house.
Okay.
Yeah, so I mean, neither of those ways is really... Well, I guess the second way is more accurate. I mean, there's no actual electron that's actually being split in two, but that's a nice way of thinking about it, really. Okay, so with me so far?
Yes. So we have our string, our superconducting nano string with no resistance. At the end of this string, so we got a party going on the string, and then we have two bouncers at either door, front door and the back door. But it's only half a bouncer. And when you have one whole bouncer, that means you have an electron, and the electron could be at the front of house or the back of the house, or not the house, the club, at the front of the club or the back of the club.
Yeah, that kind of thing.
Okay.
But just be careful. So when you have two of these Myronas, these two half bouncers,
right,
you don't necessarily have an electron in that house.
Okay.
Right?
Okay.
It could be an empty house.
Okay. So So there, you have your half bouncers that may or may not have an electron.
Yeah, they may have already let the electron in, or they might be keeping it out.
Okay.
Maybe the electron's too drunk. I don't know.
The drunk electrons. We're just kicking out the bad names today, man. We're gonna,
So in the last episode, we talked about physical manifestations of qubits, and I said that if you had some system with two states, you could call one of those states 0 and one of those states 1, and all of a sudden it looks like you've got a qubit. Right? Remember, like with the polarization of a photon,
right,
the photon could be polarized horizontally or it could be polarized vertically. And if I call one of those states 0 and one of those states 1, then it looks like I've got a qubit, and I can consider superpositions of those two states and whatnot. Well, in this current case, we've got a state of 0 electrons being in the house and a state of 1 electron being in the house, or the club or whatever. And so it kind of looks like we've got a qubit, right? Mm-hmm. And in fact, we basically do. So in reality, you need, rather than 2 Majoranas, which make 1 house, you actually need 4 Majoranas, which make 2 houses. And then say you add an electron into that system, then if my Majoranas are oriented in a square, then the electron could be in the top house, so in the house formed by the 2 halves, or the 2 Majoranas at the top of the top corners of the square, or the electron could be in the bottom house. And I'll call the former the 0 state and the latter the 1 state. Okay, so what are your thoughts on that? Is it weird? Is it natural? Is it?
It is. Well, you are introducing an electron for sure, because you were saying either they could have the electron or not. When you have 1, but now you have 2.
There's definitely an electron in. If you count all the electrons in both houses, your answer will be 1.
Okay. Yes.
Yeah.
All right. So then, how do you go about measuring that or getting the?
Okay. So, for example, maybe you want to. So you've got a qubit. So you have accepted the fact that I have 2 states here, and that means I kind of have a qubit.
Right.
And maybe I want to measure that qubit. So the way that you would do that, to extend the analogy a little bit, or the metaphor, is you would ask, is there an electron in the top house? And if the answer is yes, then you know that then that's your answer. The answer is yes, that means that the qubit is in the state 0, because we said that if the electron is in the top house, we define that as the state 0.
Right.
Now, if the answer is no, there's no electron in the top house, then because you know that there's a total of 1 electron in the system, it must be in the bottom house.
Yeah, okay.
Yeah. And so you've measured the qubit to be in the state 1. Okay, so there is another feature which is kind of cool, is that there's a really nice way of understanding the left and right arrow states of your qubit. Remember, when thinking about the qubit as an arrow pointing in space, it could be pointing up or down. That's 0 and 1. But it could be also pointing to the right or to the left, or forwards and backwards. So thinking about the right arrow state, we can conceptualize that as the electron, rather than being in the top house or the bottom house, it's in the rightmost house. So if I take the two Majoranas to the right of the square, they are both half houses. They can form a full house.
Oh, yeah.
The sort of rightmost house, and the electron is in that, then the qubit is in the right arrow state. And similarly, if the electron is in the leftmost house, then it's in the left arrow state. So maybe another way of thinking about it is...
No, I'm just like, that's like...
sorry, go ahead.
No, that seems pretty efficient. That seems pretty...
That's nice, right?
Yeah.
It's a nice way of thinking about it.
Yeah.
Yeah. Another way of thinking is that, these Majoranas are kind of sharing an electron. And the question of which Majoranas share the electron is equivalent to which state is the qubit in.
Right, yeah. So you can have really top, bottom... I'm pointing all over the place for our listeners.
which is just perfect for this auditory medium.
Yeah, yes, exactly. But I just assume...
No, pointing is great.
Picture it in your head, everybody, and I got it right. So,
that's right.
That seems handy. Does that have... So, you mentioned that as a feature. How does that play out as a feature? Exactly.
Yeah. So say that you can move these Majoranas. Now, I introduced them as being at the ends of nanowires, right? So it's a bit confusing as to how you can move them. Like, it seems like you've got a wire and they're either there or they're not.
Right.
It turns out that you can make networks of these wires, and you can kind of shuttle the Majoranas around these networks. So they're like little cars moving about in a tunnel network or something like that. And okay, so say I have this grid, this square with one electron in between the four Majoranas, and so that's again a qubit. And maybe I start with the Majoranas I start with the electron in the top two Majoranas in the upper house. Then maybe I want to change my qubit state to be pointing in the right arrow state. Yeah, I start with it pointing up, and I want to rotate it to pointing to the right. So one way that you could do that is by simply moving your Majoranas around so that the Majoranas that are sharing the electron are now located to the right of the square. So that process of taking two Majoranas and exchanging their locations is called braiding. And the connection to braids that you do with hair is a sort of extra layer, but it basically has to do with considering the paths that these particles or these Majoranas take through space-time. So we can talk about space-time and world lines and all this sort of stuff a bit later, but basically if you think about the paths through space-time that these Majoranas take, then what you find are braids and tangles and knots and things. Yeah. So, but basically, the idea is that by exchanging these two Majoranas positions, you get from the electron being in the top house to the electron being in the right house, and the effect of that is a rotation of your qubit state from the up arrow state to the right arrow state. Right. If that makes sense.
Yeah. So is that something you would control, or that's just part of the system?
That's something you would control. So that could be a gate that you perform on your qubit.
Right. Yeah. Okay.
So that's in fact one of the gates that make up a universal gate set. So remember we talked about that last time. If you have a universal set of gates, of quantum gates, then you can do any quantum algorithm that you want.
Yeah.
So you're getting kind of close to being able to do a full-on quantum computation by just moving these Majoranas around. It's very intriguing. There's another reason. So that's the reason that it's sort of nice to have this way of representing qubits. There's a more physical reason, which is that the qubits that these Majoranas store or encode are incredibly resilient to noise. The way to think about that is that when you have two states of a qubit, those two states have some energies associated with them usually. So maybe the 0 state has a lower energy to the 1 state. If you were to make a qubit in the right arrow state, you really need to know the energy difference between the 0 state and the 1 state very, very precisely to be able to keep your qubit in the right state, in the right arrow state. If you lose a bit of control over the energy difference between those two states, then that's equivalent to losing control of your qubit a little bit. So maybe some noise comes along and changes the energy a little bit of one of those states, then that can cause problems with the control that you have over your qubit. Right. So if you remember way back at the beginning of or towards the beginning of the episode, I said that when you're in this topological state, you have a 0 energy state that an electron can inhabit in your superconductor, right? That was this topological invariant that I mentioned earlier on in the episode.
Right.
So that is exactly what this analogy of these two half houses is getting at. Whenever you have these two half houses, they come together to form a full house, and that is something that the electron can reside in, right? This is the analogy that we're going with. That is the 0 energy state.
Right, yeah.
That characterizes or that sort of defines this topological phase that the nanowire can be in.
Okay.
Right? And remember, that state is at 0 energy, and there's no sort of perturbation, no small perturbation that can change the energy of that state. Right? The energy of the electron in that house. Because if it were to change it away from 0, that would be a small perturbation that changed this topological invariant, and we said that couldn't happen, right?
Mm-hmm.
So, okay, you have these two states, no electron in the house, 1 electron at the house, and they're at the same energy level, both at 0 energy, right? There's no energy difference to these two states. That effectively means that this qubit is incredibly impervious to noise. There's no noise that can come along and change the relative energies of these states and therefore mess up our control of the qubit. It's wonderfully protected.
Yeah.
Now, I sort of am skirting over a little bit of a detail here, which is that instead of being exactly at 0 energy, this state that the electron can be in, or this, the difference between these two states, is actually just very, very, very small. But the key thing is that as you move these Majoranas further and further apart, that difference between the two energy states gets exponentially smaller.
Okay.
That is to say that as I move these Majoranas further and further apart, or equivalently, as I grow the length of my nanowire, the level of protection that our qubit has against noise gets exponentially better.
Right.
So I can make as good a qubit as I want. I can have as good a control over my qubit as I want by just making, by moving these Majoranas further and further apart.
Yeah.
So that's the sort of way in which it's resilient to noise. So that's why these systems are so exciting as potential avenues for quantum computation.
So can you give me a sense of the scale that you're talking about by moving them apart?
Ooh, yeah. I'm going to say micrometer scale is the maximum. Again, because I'm in the world of theory, I don't need to worry too much about materials or length scales or anything as much as the next person. So I've just found something here which seems to suggest that the length needs to be sort of much larger than 100 nanometers, so maybe on the order of a few micrometers.
Right.
And in the thickness is going to be really small in comparison to 100 nanometers, so on the order of tens of nanometers maybe.
Pretty tiny.
Pretty tiny, yeah. I mean, so we talk about these vast distances between the Majoranas, and so they're basically on top of each other from our perspective, from everyday perspective.
Just keep your quantum computer in your back pocket. Bring it wherever you go.
That's it, yeah. Yeah. So that's computing with Majoranas.
Yeah. So I guess final question to you. I mean, this is where your head is at. This is your research. This is what you're studying. You've made the case. It seems like there's a lot of good features to this. What is the issue with implementing this? Is it really
the main drawback?
Or does it really come down to this? How do you set this up in nature? Is it really?
Yeah, I mean, so there is what's called a reproducibility crisis. So this is something that's kind of popping up in a lot of areas of science over maybe the past decade or 2 decades or something like that. And so, there's a mini one going on with the experimental Majorana field. So people that have, or groups that have published papers in very high impact journals like Nature and Science that have supposedly found features of these Majorana fermions, basically found these two states with the same energy, these two zero energy states. And they purported to find these, and then it turned out later that there had been some fudging of the data. You can sort of debate as to whether or not that means that there's been actual solid evidence of Majoranas discovered to date, and I think that there is still good evidence that they have been discovered in labs, but I think some people do disagree with that.
Right.
And that does sort of give a little pause for thought,
right,
for those of us in the field. Have they been discovered? Is this actually worth the time and investment to continue pursuing? For example, there's no question that we've built qubits in labs in other ways.
Yeah.
There is certainly a question as to whether or not we've found Majoranas. So yes, that's definitely a drawback. It's a much longer term project.
Yeah.
There are also drawbacks on the longer term scale. Even if we do have a huge number of Majoranas that we can closely control and braid with one another and do all these nice things that we would like to do, unfortunately, braiding doesn't get us a universal quantum gate set like we would like. We would want to be able to do braiding in order to perform a universal set of gates, because remember, we can keep the Majoranas really far apart through that whole braiding process. If I exchange two Majoranas, I can, they can be very far apart through the whole process. And that means that the qubit can be resilient to noise throughout that whole process. And the rotation that we perform by doing that braid of the qubit arrow, remember, from up to right, that rotation is very precise. So it would be lovely if we could do the entire computation by just braiding Majoranas. Unfortunately, they don't quite work that way. So you need to supplement it with extra steps, and those extra steps are not as resilient to noise. Right.
Yeah. If you need to rely on the standard, I'm air quoting, standard quantum computer here, you're kind of just introducing a step back, a link in the chain that is susceptible to all that noise and all the problems you're trying to solve in the first place.
Exactly. So you might say, well, if there is a link in the chain that isn't as strong as the other ones, well, the chain is only as strong as its weakest link. So what's the point? Why bother? But there are ways that you can combat those steps. So it is still useful to have these things that you can do that are resilient to noise. It's useful to have certain gates that you can implement by braiding. And there is also just the fact that these qubits, if you're just letting them sit there in their state and you're not doing anything to them, well, they are very impervious to noise. There are also caveats even to that statement, unfortunately. But we can leave it idealistically.
I didn't mean to end it on such a downer, but no, because it sounds fascinating. I mean, it really,
Yeah, I mean, I think a few years ago, when I first heard about this field this model of quantum computing, which involved braiding, which involved moving particles around one another, that was just incredible to me. I thought that was so amazing and bizarre and counterintuitive. So I was very excited to have the opportunity to work on it.
Yeah, and that's I again, like, I do a little bit of reading on this stuff, and and that's one of the things you always hear about, whether it's Google or Microsoft or whomever, they have a problem with the noise. They have the device, but it's not doing what they needed to do. So to have a way that takes care of that, to have a method and a potential way to build that it's exciting. It's
very exciting. Yeah, I think so. And so does Microsoft, because Microsoft is investing in this type of quantum computing.
Really?
Actually.
Wow. I cannot wait for my Xbox to be able to do some quantum computing, and it gotta keep it in the refrigerator so it stays nice and cool.
Yeah. But if you have some liquid helium around, that will be that'll be useful for that.
But the ray tracing
Yeah.
will be amazing.
That's right.
Campbell, thank you for letting me talk your ear off, as always.
I think it's been a little bit the other way around, so apologies if your ear is falling on the floor,
Well,
dear listener, or Brian.
again, ladies and gentlemen, if you have any questions for us, any follow-up questions, please send them to our email, which we've definitely set up. It's in the description, so why would we have to say it?
And as we said last time, we are going to respond to your questions, but if you asked a question on the first episode, like after listening to the first episode, and it's gotten to whatever episode this is now, then then be patient, because we have pre-recorded these, so we will be getting to questions soon.
Yeah, absolutely. Anyway, that has been this edition of Question Field. Again, the place where you will ask the questions, and we will field them, and we will see you next time. Have a good one.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars, located in the review section of your favorite podcast app. Thank you for listening.